Okay, we will start our lectures from now on. Okay, everybody hear me, right? Everybody? Yes?
Yes.
Yes. Okay, I think all of you already familiar with the teachings. We are online. Okay, so should not have any problem except you have a problem on the internet connections. Okay, anyway, we will start first with the course syllabus. Okay, uh, you are lucky because this will be the last teaching course because there is a new curriculum, right? That this subject is no longer in that new curriculum, and that the reason why I have to teach 2 classes in this semester for the ISE. This class will be replaced by the new ones called the modern propulsion system. Right? So you are the last generations that will learn on these internal combustion engines, right? The wholly internal combustion engines. Okay, so let's look at our course syllabus. We'll talk about the internal combustions according to this course descriptions, but there are some a little bit modifications, but we will go almost 95% cover for this course descriptions. Okay, I think the rest you can read it by yourself. Let's go to our schedule. We will have the lecture every week, and our lecture will go by this schedule. Okay, so you have to arrange your time, right, according to this schedule so that you can attend the class all the time. The midterm is expected to have on 8 to 12 of March, so it's about 2 months from now. So don't be careless because time flying fast. Okay, so it's better to prepare early. Okay, we will talk on the class schedule. We will talk about the engine type and operations for about 2 weeks, and then we will go for the engine design, operating parameter, and also the induction and the exhaust. All of these 3 lectures already in my course view. Right. Last night I replaced the first lecture with the new one because I found some error over there. So you better load the new one, the lectures underscore 1_news. Okay, that's the new lectures that I just downloaded last night. And then we will talk about the fuel combustions in the 4th week and air standard and fuel cycles, right? These 2 lectures I think all of you already familiar with because these 2 lectures is already in the thermodynamics. Right? Some portion of this 2 lectures is already in the thermodynamics. And then we will have a fuel meterings, right? Because the fuel have to be metered before it's sending into the cylinders. And then the combustion happen. That's why we follow up with the combustions after fuel get into the engines, right? But the combustion can happen only when we have an ignition system, right? And then because of the combustion, it creates the emissions. Right? This is the result of the combustion. So we have to learn about the emissions and how to control the emission that happen due to the combustions. Right? And again, because of the combustions, we have the heat transfer that happen, right? Because this internal combustion engine is, in fact, is a heat engine where we have to provide the heat, right? The heat come out from where? Originally come out from fuel, and then we combust the fuel. It will create the heat for us, right? So we have the heat input to the engines, and then what is the result? The result is the work that come out from the engines. Right? That is the reason why we call it the heat engine. Okay, and because there's a lot of movement inside our engines, So we have to talk about friction and the lubrications. Okay. Yeah. Unfortunately, that 14 April is a holiday, right? So we will announce the backup class later on. It may be, I look through my schedule, it's very tight. It may be on Saturday or it may be on the evening. Let's see what we can do on this makeup class later on. Okay, and then we will talk about the superchargings and turbocharging, right, in order to increase the powers of the engines. Right, this is the way that we can increase the power of the engine without increasing the size of the engine. Okay, and we will round up everything with the testing and the performance of the internal combustion engine, because when we build up the engine, we have to test it, right, in order to see how much is the performance of the engine that we built. Okay. Okay, and the assessment or the grading in this class, right? We will have a midterm for the 45% and the final exam for the 45%, and the homework is about 10%, right? I forgot to talk about the homework. The homework is right here on the assignments column, right? Start from next week, we will have homework number 1, and the homework will go on and on every week, right? And you can see in the schedule, right? We will have 12 homework all together. Okay. The grading criteria, I think most of you concerned, right? It's very clear cut here, right? When you read the grading criteria here. I would like to ask someone to close your microphone if you are not talking. I hear the voice, it's a disturbing voice. Okay, thank you. Okay. The total score, if you can get more than or 80%, okay, 80% and more than 80% from 100, you will get an A, definitely, no questions. Okay. And if you get less than 30%, which I do not, I hope that you do not get less than 30% because the homework is already 10%, right? So you just accumulate the knowledge of this subject for about 20%, then you will not get an F, right? 20% from 100 knowledge. Okay, so I think this is quite comfortable, right? Not so difficult. Okay. The textbook, of course, is a handout. Right? Every week, I will give you a handout, right? Not only for this lecture notes, but also some other materials. Right? For the supplementary books, right? You can get it from these 2 books. Right? The first one is the Internal Combustion Engine Fundamentals, and the second one is the Engineering Fundamental of the Internal Combustion Engines. Right? You can try to get this book in the internet for free, but if you cannot get it, just ask me, right? Because I don't want to put it in my course fields. Okay, so that is the overall course syllabus. Okay, that we have to follow for this course. Any questions for the course syllabus? Any questions? Clear. Okay. So if no question, we will start on our first lectures. Okay, let me share you my lecture note. Okay. 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 Okay, we will first talk on the engine types and operations. Right. In general, there are 2 types of the engine. Right. This 2 types of the engine we classify according to the heat is transferred to the engine. Right. How the heat is transferred to the engine. Okay. The first type is called the internal combustion engine. For the internal combustion engines, the heat is transferred to the combustions, right, that occur in the working fluid. So the combustions happen to the working fluids. So this is called the internal combustion engine. And when combustion happens, we get the heat. Okay, there is only one cycle for this internal combustion engine. Right? It is an open cycle because the working fluid is combust. So the working fluid have to refill or replenish, right, in each operating cycle because it is combust, right? And when it's combusted, we have to exhaust or release it out. So every time that the cycle is operate, we have to refill the working fluid all the time. Okay, right. So this is called the open cycles. Right? The working fluid will change into the exhaust gas after combustions, and we have to release it to the atmosphere. I cannot change this because someone entering to the meeting, and then I cannot change this. Okay, let me share to you again. Okay, that's the problem of the Zoom. If someone entering and leaving during lectures, right, the PowerPoint gets stuck. Okay. Okay, the second type is the external combustion engines. Internal combustion engines, right? For this type of the engine, we need to have a heat exchangers, right? This heat exchanger is used to do what? To transfer the heat or the energy to the working fluid. Right? So that means what? The working fluid will not change, right? Because the working fluid is only used to receive the heat from outside, right? And we will let this working fluid to work in our engines to create the work. Okay, so this type of the external combustion engines, right, we have two cycles. The first one is the open cycles, right? The open cycle, the example of the open cycle is a reciprocating steam engine, right? In which I show you the picture here. This is the very old type of the engine, or the engine at the very beginning of our industry. Okay, in this picture, you can see that we will let the steam to flow in, right? So this steam come out from water. The water receive the heat, right? So we provide the heat to the water, and the water become the steam. And after it become the steam, we let it flow into our engines, right? And when it flow into the engine, right, we will let it keep flowing into our cylinder here, in which we have a piston inside. So the steam will move the piston, right? The steam color is the pink one, right? The steam flow into the cylinder. This is called the double acting because the steam can flow in two ways, back, front and back, right? So that's why they call it a double acting, right? That means every time that the piston move, it will create the work, no matter it move left or right, right? Because the steam will flow in the left, in the right, and in the left. Okay. And when the steam, after the steam pushing the piston, right, you can see that another portion of the steam that behind the piston will be released out. Right? So the steam, we have to keep providing the steam to this engine all the time. Right? So that is called the open cycle. That is the reason why we call it open cycle. Right? And most of the engine require a lag and pinion mechanism. Right? Lag and pinion mechanism is a mechanism that used to provide to convert what? You can see that the piston move in linear motions, right? But the wheel move in rotational motions, right? So we need a mechanism to change the linear motions into rotational motions, and that mechanism is called a lag and pinions. Right? I will show you in more detail of this mechanism later on. Okay. Another cycle that can be external combustion engines is the Stirling engine. Right? The Stirling engine look like this, right? In which you can see that we don't have any working fluid come out from our cycle. Our working fluid is always contained in the cycles. No way to come out. Right? And that's the reason why they call it the closed cycles. Right? It keep moving up and down, up and down. Right? It moves, right? Because of the heat that we provide. Right? The heat that we provide here. Right? So when we provide the heat, the working fluid will change, right? And it will create the power to push the piston. And after it finish pushing the piston, right, it will release the heat out, right, and then receive another heat again and get the power again. Right. It will go like this on and on. So how the work come out, we will talk about later when we go for the PV diagram show right here. Okay, but let's first look at the PV diagram of the reciprocating steam engine. Right. I put a notice here that when you look at the PV diagram, this is the PV diagram that they put inside the steam engine. Right. You can see that there is no combustion happen, right, on the PV diagram of the steam engine. Right. It will have only compressions. Right. The compression start from here and finish up here. Right. Where combustion happen, where compression happen, the steam is starting to refill into our steam engine. Right. Until finish here, right, the steam is cut off, no more steam flow into, then the expansion happen. Right. The expansion happen. And the expansion will stop right here where the exhaust happen. The exhaust means we are relieving the steam out of our cylinders. Right. And then it start compress again. Okay. So this is the PV diagram in which the area enclosed here, or the enclosed area here, is represent what? Is represent the amount of work that done by these cycles, because this is the pressure and the volume diagram, right? So if we perform the integrations over this enclosed area, it's gonna be the network that come out from the steam. Okay. How about the Stirling cycles on the PV diagram? Right. For the Stirling cycle, you have only two processes that happen. The first one is the isothermal process. The second one is the heat transfer process. For the isothermal process, we have isothermal compressions, which compress the working fluid inside the cycles. Right? It is called isothermal compression process. And then we give them the heat. Right? So it's compressed, get the heat right here. And then after it get the heat, right, we will have another isothermal process, which is called the isothermal expansions, because it's compressed right here, get the heat here, and then go to expand here, right? And after expand, it fall back, right, to release the heat out, Okay. Theoretically, these two heat in and out happen on the isochoric process, which is the constant volume process, right? But you can see that on these animations, there is no actual constant volume happen, right? So the actual process will be different from this graph because our engine have to move all the time. So it's no way that it will have the constant volume process happen. Okay. How about the amount of work? The amount of work come out from where? Right? You can see that the amount of heat that flow in equal to the amount of heat that flow out. Right? Heat in always equal to heat out. So where is the amount of work that come out? The work come out from the isothermal process. These two isothermal process, right? With it have the heat transfer. Right? Even though the temperature is presumably to be a constant temperature, but the heat can transfer, right? So we have the amount of heat come out from expansions, the amount of work come out from the expansions and the compressions. Right? The difference of these two will represent the amount of work. Okay. And because theoretically the amount of heat in equal to the amount of heat out, right? So in theory, these cycles or these stirring engines, we need to provide just only one amount of heat. We provide only one-time energies to these cycles, right? And the same amount of energy will release out from the engines. So we can use this energy to feed it back to the stirring engines. Okay, so this by theoretical, right? It requires only one amount of heat to run the cycle, and we can keep this heat to go on and on in the cycles, right? In order to make the cycle go on and on. Okay. Okay, so that is the two types of the engine, right? The internal ones and the external ones. Okay, so this graph or this picture gives you the whole ideas, right? What are the engine that is classified as the external combustion engine, and what are the engine that classify as the internal combustion engine, apart from that we just mentioned. Right? On the internal combustion engine, okay, we have the steam engine already mentioned. We also have the steam turbine engine. Right? That is not a reciprocating engine, but we have a turbine. Right? Steam will run the turbine, and the turbine will go to the wheels to create the motions. Right? We also have the hot air engine reciprocating. That means instead of using steam, we provide the heat to the air and let the hot air go into the engine, right, to create the motions. We also have a closed cycle gas turbine, engines that we provide the heat through the heat exchangers, and we let the working fluid inside the gas turbine cycle to receive this heat and flow into the cycles. Okay. On this portion, the internal combustion engines, we have the rotary engines, we have the rocket, and we have a reciprocating engines. Right? For the rotary engine, right, we do have the open cycle gas turbine, right, which is different from the closed cycle gas turbine. Right? Because for the closed cycle, the working fluid will never leave the cycles. But for the open cycles, right, the working fluid will leave the cycles. Right? We have to refill the working fluid. Okay. We have the jet engines. Okay, this is also the gas turbine engines. Right? But when we mention about the gas turbine here, right, it means we have work come out from the gas turbine. But for the jet engine, we're talking about the gas turbine engines that provide the thrust force, not the work come out. It provide the thrust force in order to push the plane to fly. Okay, we have the Wankel engine. This is another displacement type or the reciprocating engine, but it's not using the cylinder and the piston. It used the rotor. So it was pushed into this category, a rotary engines. Okay. For the rocket, we have the ram jets and the power jets. Right? Okay. This rocket have only combustion chamber, right? And it have a very high heat during combustion in order to get the powerful exhaust to come out. Right? So this powerful exhaust will create a very high amount of thrust force, right, to push the plane or the rocket to fly. Okay, and then come the reciprocating engines. This is our main concern here. Right? This class will talk mainly on this type of the engine, the reciprocating engine, which is classified into 4 different engines, but we will talk only on the diesels and the petrol. Petrol is the gasoline or the benzene. Okay, so we have benzene and we have diesel here. Okay, another 2, right? In fact, it can be classified as diesel or the petrol engine as well, but only the difference is that for this type of engine, you can use more than one kind of the fuels. Right? They call it a multi-fuel engine, but commercially, you probably can see the flexible engine. Right? When people mention about the flexible engine, it means that engine can use fuel more than one type. Right? It can either use, for example, the gasoline or the gasohol or even the natural gas or the LPG. Okay. Okay. And another one, this is the gas engine. Right? This is the engine that use only gas fuels. Right? That's why they call it the gas engine. Right? They can run by using the gas. Okay. Okay, so we know about the type of the engine already. So now let's get into our business. Okay. Start with the history of how the engine is developed. Okay. Everything started in 1860. 1860. So it's about what? 160 years ago, right? So that we start to have the engines. The first engine is called Renoir engines. Right? Renoir is the name of the French engineer, right, who invented these engines. Right? This Renoir engine, right, there is no compression state like the engine nowadays, right? That like the engine that we know nowadays. Right? We know that the cycle of the engine, the first process have to be the compression process. But for this Renoir engine, there is no compressions, right? But they do have combustions, right? So no compression before they have a combustion process. Right? This is the first engine. So the engine character is what? Both air and fuel were hand pumped. Wow. So it pumped by hand, right? We send the mixtures or the air and fuel, right, to flow into the engine by using a hand pump. Okay. And the spark or ignitions was done by what? A candle or a kerosene lamp, right? And it's even more amazing. All of these are done by hand. So you can imagine how dangerous it is to run this engine, right? It means you have to hold the candle in your hand and then insert the candle into the cylinder of the engine every time that you need the combustion to happen. Okay. And you can do this. That means you can ignite by hand because the engine run in a very slow motions, right? Only 10 rounds per minute, right? So that's why you can do it by hand, right? Only 10 rounds per minute. So you can imagine how slow it is when compared with the engine nowadays. Okay. And it is a two-stroke engine. Right. What is the meaning of the two-stroke engine? I put it right here in the blanket. That means everything in the cycles will finish in one crank revolution. Right? So the crank will rotate only one round in order to finish the cycle that happened in this engine. Okay. And in order to keep this engine running, right, the ignition that happened, right, it happened even the cycle is in the expansion state here, right? For the modern engine, right, this fact is still this thing is still the fact that happened for the modern engine, but it occurred in a much shorter time during the expansion state, but not like the Renault engine that this ignition still happen in the expansion state for a longer time. But for the modern engine, some engine, the ignition still happen during the expansion state, but in a shorter time. Okay. And this engine was sold 5,000 units at that time. Right. Okay. Look at what are the process that happen in the Renault engines. Right. I show you here for both the PV diagram and the TS diagram here. Okay. This is the theoretical diagram, right? And another slide, I will show you the actual diagram that happened. Okay. Theoretically, right, everything starts on the isochloric process or the constant volume heat additions, right? So we provide the air and fuel mixture at the constant volume here. Okay. And the ignition happened. Right? So the expansion happened follow. Right? It is the isentropic expansions. And then after finish the expansions, then we have a constant pressure heat rejections where we release the amount of the exhaust. Right? We release the exhaust out here and then we refill the air fuel mixture and then ignite in order to create the combustions, and then the expansion happen, and then we release the amount of the exhaust again here. Okay, so this is on the PV diagram. How about on the TS diagram or the temperature and the entropy? Right. You can see that we start right here with the isochloric process heat transfer, right? So the air fuel mixture provide along this line, and then ignition happen. We have the isothermal process, isentropic expansion process happen here. and then we have another constant pressure heat rejection here, right? Okay, so what are the difference between these two, right? This one I already mentioned. The enclosed area here represent what? The network that happened, right? So this enclosed area represent the network that happened off from the cycles. How about on the TS diagram here? The TS diagram here, the enclosed area represent the amount of heat, right? The net heat that happened to the cycles, right? So by the first law of the cycles, if everyone still remember, the first law of the cycle, the first law of thermodynamics for the cycle tell us that the net amount of work equal to the net amount of heat, right? So the area enclosed here have to be equal to the area enclosed here. Only that this PV diagram have nothing to tell us about the heat. And on the TS diagram here has nothing to tell us the amount of work. Okay, but both are related to each other according to the first law of thermodynamics for the cycles. Okay, and since usually we want to find the amount of work, right? And we want to find it easily. So mostly we prefer to find the amount of work from the amount of heat, right? So for this engine, you can find the amount of heat from these two equations, right? The heat that adds to the engine happen at constant volume, right? So we can use the specific heat at the constant volume times with the difference between these two temperatures, right? And the amount of heat that released in terms of exhaust that out from the engine is represented by QL, right? Which is the heat rejected. It happened at the constant pressures, right? And happen between these two temperatures, 33 minus 31. Okay. So by these two expressions, right, we can determine the amount of work that come out from the engine, right? How about the efficiency? Right, it is W divided by QS, right? So the efficiency is a little bit complicated form, not the easy form, simple form, right? Because it involves with the term of gamma or the K value in the thermodynamics, which is represent what? The ratio of the specific heat at the constant pressure to the ratio of the specific heat at the constant volume. Okay. How about the actual cycles? Okay, the actual cycle look like this. The actual cycle look like this. Okay, in which you can see when we make a plot on the PV diagram, you don't see any constant volume happen in the cycles. As I already mentioned, because the piston move all the time. So you don't see the constant volume happen, right? But if you want to compare with the theoretical one, the constant volume heat transfer happen right here in a short period of time. Okay, and in the small change of the volume. Okay, and then ignition happen right here. Right? Why the piston is start moving down. Right? The piston start moving down. That's why you see the volume increase. Okay. Here, the piston start moving up. Right. So you can see the change of the volume, and then it's moving down, and then it's moving up again. You see the reduction of the volume here. in order to release the exhaust out. Okay, so this color line represents the diagram, the actual diagram of the Renault. And in this diagram here, you can see that the Renault engine have a very limited expansion ratio, right? Very limited one, from here to here. Okay, and that result in a very low efficiency, less than 5% for this engine. Right? Compare with the Otto cycles or the benzene or the gasoline engine, that they do have more expansion ratio. Right? So the Otto engine have a higher efficiency, right? Because of the higher expansion ratio here that happened. Okay, and then, right, 7 years later, right, we start to have the Otto engine. Right? Otto is the same name of the engineer called Nicholas. Right? He's a German engineer. Right? 7 years later, and this engine used a lag and pinion flywheel as a crank. Right? And this shows you the mechanism of the lag and pinion. Right? This is called pinion. This is called a lag. Right? You can see that the pinion will rotate, so it have a rotational motion. The legs, right, move in the linear direction, so it have a linear motion here. Okay, so the Otto engine use lag and pinion flywheel as a crank. This is the flywheel, the big flywheel here. Right. Okay, this flywheel is considered to be a mechanical battery because this flywheel is used to restore the energies. The reason why Otto need this flywheel, because Otto use a 4-stroke engine. Right? Renault use a 2-stroke engine, and by 2-stroke engine, it means what? You have power come out every time that you finish the cycle like this. Every time you have power come out, right? So you don't need a big flywheel like the Otto engine, right? But for the Otto, they use a 4-stroke. That means the cycle have to finish into crank revolution, or the crank have to move 2 rounds in order to finish the cycle, right? But unfortunately, there is only one powers happen, right, in 1 round. Another round of revolution, they have no power come out. So how, in order to keep another round to keep rotating, right, they need the powers, right? And this flywheel will be used to provide the power to that round, that no power cycle happen. Okay, this happened to the present engine also, right? Every engine need a flywheel, right, in order to provide the power to 1 round of revolution that there is no powers happen. Okay, so it's a 4-stroke engine, right? And as I already mentioned, it have higher expansion ratio. So the efficiency was better than Renault, right? It's about 11% at that time. And then 25 years later, in 1892, another engineer from Germany called Rudolf Diesel, right? He invented the diesel engines, right? This diesel engine is different from the Otto cycle, in which it will injecting the fuel into the air, right? It different from the first 2 one where we mix the air and fuel together before we send it into the cylinder. But for diesel engine, they send the air that is compressed, right, already into the cylinder. So we have the hot air waiting for the fuel inside the cylinder, and then we inject the fuel into the air. So the combustion happens without any ignition. No need to ignite because the fuel encounter with the hot air in a limited space, right? So it automatically combusts, right? No need to have any spark plug or no need to have any ignitions. Okay, so that's why he can name this engine a diesel engine, because different principles. And the efficiency was double from that auto engine, right? Auto is about 11, so diesel is about 22. Right? And then in 1957, right, another engineer called Wankel, right, invent a rotary engine. Right? That means this engineer is no longer see the picture of the cylinder and the piston, right? Because with cylinder and piston, he have to change the linear motion into the rotational motion by using a lag and pinion, right? So he think why we do not create a rotary motion happen in our cylinders, right? So we no need to use a lag and pinion to change this rotational motion into a rotational motion. You need to change the linear motion into the rotational motion. So the Wankel engine come up, right? Because you can see that the cylinder, the piston is replaced by the rotor here, and the rotor is rotating within the cylinder here. Okay, this picture, I just want to show you that this is the famous engine at the very beginning of the engine history. It's called the charter engines, very successful gasoline engine here, right? And it's when it's what used in the farm, not on the road, right? Because it was very big, right? So it's widely used in the farm. Okay, look at the other development. In 1870, the petroleum industry started, and I put in the bracket here, 10 years after the Renault engine. So the question is, what are the fuel that used for the Renault engines and even for the Otto engine at the very beginning? Anyone can give me some idea of the fuel that used in the very beginning of the engine in history? Hello? Hello? Anybody? Anyone can give me the idea of what are the fuel that used in the engines for both Renault and Otto engine in the very beginning? Because the oil just come out in 1870, 10 years after the Renault engines. What are the fuel that we use? Hello ได้ยินไหมได้ยินไหมครับอู้ฮัลโหลฮัลโหลไม่ได้ยินเหรอ
ได้ยินครับ
อ้าวแล้วไม่ตอบอ่ะ ถ้าไม่รู้ก็บอกว่าไม่รู้นะ if you don't know just say no I don't know so that I will give you the answers. I just ask to get your attention only, but do not expect that you can give me the answers. Okay, but just ask for your attention only. Okay. So next time if I ask and you don't know the answer, just say I don't know. Okay, that's very easy. Okay. Okay, so the fuel that we use is the vegetable oils that used mostly in the house. Right, that's very simple. Okay, so it's so we have no question or no wonder why now we come back to the vegetable oil, right? We go for the the gasohol, right? The fuel that come from the plant, right? Right. That we produce the fuel from the plant, right? Such as the methyl alcohol, right? For example, okay. So in 1870, the petroleum industry start, and then in 1888, we start to have a pneumatic tire. So that means before that, all the tires are solid one, right? Are solid, not the air-filled tire as the present day. Okay, and 1905, we start to have the spark plug. So you can imagine that we still use what? The candles and the kerosene lamp before that, right? Until 1905, we invent the spark plug. And the company that invent the spark plug is called the Champion Company. It still have, the company is still doing their business nowadays, right? The Champion spark plug. Okay. And in 1920, right, this is the time that the internal combustion engine start to take over the steam engine for transportation. Right? If you remember, right, we have the steam engine at the very beginning, right, and it occupied the market, right, until 1920, right, the internal combustion engine start to take over the market, right, or start to kick out the steam engine out from the market in terms of transportation, right? Due to the main advantage that the internal combustion engine has, right? Because it no need to carry around the water, right? Like the steam engine. For the steam engine, you need to carry water. Remember, it's an open cycle, right? The steam flow out. Okay, you need to carry the coal, right, in order to burn and keep the heat to the water. Okay, get stuck again. Okay, get stuck again. I cannot move the slide. Okay. Okay, so, and then in 1970, 1920 to 1960, right? This is the golden years of the ICE because they have a steady development in the internal combustion engine, right? Because the market, more and more that the market start to accept this kind of engines, right? So it's a golden year. People make money from the internal combustion engine. After that, what happened is what people start to recognize about the emissions that come out from the engine, right? The first person that recognized about this is called Professor Hagen Smith, right? Because he found the smoke mechanisms. The smoke mechanism is what? It is the reactions between the oxides of the nitrogens and the hydrocarbon compound. Right? These reactions between these two happen because of the sunlight. So imagine who emits the oxide of the nitrogen and also the hydrocarbon carbon compound. It is the engine, right? Due to combustions, it have the nitrogen oxide come out, right? Because this is one of the product of combustions, right? And then how about the hydrocarbon compound? This is the leftover of the unburned fuel that come out in the exhaust. Not all 100% of the fuel that you inject into the combustion chamber, all of them will be combusted, right? There is a tiny amount of the hydrocarbon that left over from the combustions, right? And it's fall out with the exhaust. So these two flow out into the atmosphere, and then the sunlight come in and make these two react with each other. So the smoke happen. Okay, so this is the first problem that encountered on the use of the internal combustion engine in 1960. Another one that affects the internal combustion engine is 1970, where we have the fuel crisis, right? This year is the starting year of the OPEC, right? I think everybody know about the OPEC, right? Okay, so there's a large fuel supply shortage happen all over the world. Okay, so people start to recognize the efficiency of the internal combustion engine. They need to improve the efficiency of the internal combustion engine in order to reduce the amount of the fuel consumptions. So start from 1980, right? All over the world start to compete about the engine improvement, right? About the engine improvement. And then another problem hit the internal combustion engine. And this is the biggest one, because in 1990, people start to recognize the greenhouse gases. Greenhouse gases involved with what? Involved with the carbon dioxide, right? When we do the combustion, it's always have carbon dioxide. And carbon dioxide is considered to be one of the greenhouse gases that will create the global warming problem, right? So they have to, people in this industry have to think about how to make the combustion go for higher and higher efficiency and higher effectiveness in combustions, right? But no matter they go, right, they cannot eliminate the carbon dioxide that come out, right? So the way they do is they start to think about new fuel. We call it the alternative fuel or the clean fuel, right? Before that, people think only on the liquid fuels. They do not think about the gas fuels, right? And the only one fuel that they think is the fuel that comes from the crude oil, because that is the most powerful fuels, right? It gives the engine higher powers, right? They do not think about the impact that happened by using that fuel, right? But after the greenhouse problem happened, right, they have to look for an alternative fuel. Not only the fuel from the crude oil, right? They have to look out for the fuel from other sources, right? Including the fuel that is in the gas phase, right? All of this they do in order to reduce the amount of the CO2. Right? As I mentioned, they cannot eliminate, right? What they can do is just to reduce the amount of the CO2 that come out from the combustions. Okay, so this is the smog happened in LA a long time ago, right? But now no more. But if we do not do anything, right, it will be right here waiting for you in the futures, right? This is smoke. And this is the greenhouse gases that you can see. Carbon dioxide occupy for 57% of the greenhouse gas, right? And there are also other greenhouse that are considered to be a greenhouse gases, like the nitrous oxide here, the methane. Methane come out from where? It come out from the rice fields, okay? And we have carbon dioxide that form the plants, right? Biomass here, and carbon dioxide from others, right? But the most one is the carbon dioxide come out from the fossil fuel use. Fossil fuel use is the petroleum fuels that we use nowadays. Okay. That's why they have to go for alternative fuels. Okay, so that is the history of the engines. Let's look at the engine classification in more details. Right? At the beginning, we said we have two types of the engine. That is the major type of the engine, external and internal. Now, if we concentrate on the internal combustion engine, right, the internal combustion engine can be classified into 12 categories. Okay, the first one, if we look at the applications, right, the engine can be used on the automotive, on the aircraft, on the ship, or on the generator. Okay, this is according to application, right? We can use the engine to do this, to do this, to do this. Okay. The second classification is on the basic engine design, right? We can have the engine in the form of piston and cylinder. We can have the engine in the form of rotor and cylinders. Okay. Classify according to the working cycles. Right? We can have either 4-stroke engine and 2-stroke engines. Right? And for the 4-stroke engine, we can have the engine draw the air by itself, which is called naturally aspirated engine, or we have some device to help the engine to draw the air into the engine. This is called the supercharged or the turbocharged engines. Okay. For the 2-stroke engine, right, we have a crankcase scavenge. Right? Crankcase scavenge. Scavenge means exchange. Okay, exchange the fluid. Right. So crankcase scavenge means since we have to fill in the working fluid and we have to exhaust the working fluid. Right. So there are many ways to scavenge this fluid. Right. So the crankcase scavenge is the way to push the exhaust gas and draw in the fresh air or the air fuel mixture through the crankcase operation. Because crankcase is rotating, so we use this operation to push the exhaust or the useless working fluid out and bring in a more useful working fluid, which is the fresh air if it's a diesel, or the air fuel mixture if it's a gasoline engine. Right. The 2-stroke also have the supercharged and the turbocharged engine as well. Right. 2-stroke engine is hardly seen in the engine nowadays because it have a big problem about the emissions, right, that hardly be sold. Okay. Okay. This 4-stroke or 2-stroke engine can be either the auto engine, right, the gasoline engine, or the diesel engine, or the dual combustion engine. We call it the semi-diesel cycles, right? We will talk about this later on, right? For the Otto cycle, right, it is a constant volume cycle, if you remember, right, in thermodynamics. For the diesel engine, it is a constant pressure cycles here. Okay. Okay. We can also classify the internal combustion engine according to what? The valve or port design and locations, such as we can put the valve in the overhead, we can put the valve in the underhead. This valve is used for what? Okay, this valve is used for bringing in the mixture or the air fuel mixtures and release the exhaust out, right? It have to flow through the valve, right? So we can classify the engine according to the valve positions or the type of valve, right? Such as rotary valve here. Sometimes we do not use valve, right? We can use a port or the opening, right? Just an opening to let the exhaust flow out or the fresh air or the air fuel mixture to flow in, right? So we have a cross scarvent porting, a loop scarvent porting, right? Or a uniflow or two scarvent porting. Okay, but we will talk about it later on. Okay, we can also classify the engine according to the method of mixture preparations. Right? That means how we gonna mix. What are the way that we mix the air fuel together? Right? We can do it by using the carburations, right? Or the carburetor, the device called carburetor, or we can use the fuel injection by using a device called injector. Okay, this is the way we can do the mixture preparations. Okay, we can also classify according to the method of ignitions, right? We need the spark plug to ignite, or we need just compression to ignite. Okay, for the spark plug ignitions, right, we talk about the auto engine. For the compression ignition, we will talk about the diesel engine. We can classify according to the combustion chamber design, right? How we design the combustion chamber or the cylinder inside the engines, right? It can be the open chambers, it can be the divided chambers, right? So I show you this picture. This is the open chamber. That means we have only one chamber on the top of the piston. This is the cylinder. This is the piston. So the space that we consider a chamber is the space on top of the piston right here. Okay. Or we can have a divided chamber, right? Divided chamber, that means we can have more than one chamber, right? So that this one, I show you the two chamber here, right? We have a one chamber that directly above the piston. This is called the main chamber, right? And we can have the secondary chamber on the top of the main chamber where the combustion really happened right here, right? The actual combustion happened right here. And then the exhaust or the product of the combustion will flow into the main combustion chamber in order to push the piston to go. Okay, so this is called the divided chamber. Okay, we also have other type of the open chambers, right? When we talk about the open chamber, it means one chambers. Okay, remember? So other type of the open chamber are what? We have a T head type chamber where the valve is positioned along the sides of the cylinders. Right? We have the L type head, L head type here, where the valve is only on one side, right? Either the intake valve or the exhaust valve. They only on one side of the cylinder, not on both sides of the cylinder here, right? We have also another L head type here, the same, right? Valve is on the side of the cylinders, but the spark plug move overhead of the valve, not overhead of the chambers. Okay. We have the I head type of the valves where the valve is located above the chambers. Okay. We also have F head type, right, where the intake valve is on the sides and the exhaust valve is on the above of the chamber. Okay. Okay. Another classification is called the load control method, right? the load control method, how we control the load on the engines, right? We can use either by using the throttling process of the fuel and air together. That means we'll control the amount of the fuel and air together through the throttling valve. Okay. Throttling mean หลีในภาษาไทย Okay. That means we will control both fuel and air together, or we can control the fuel amount alone. This is done in the diesel engines, or combination of these two. That means we control both the fuel and air in the same time, and later on we control just amount of the fuel. Okay, this is the method to control the loading to the engine. Okay. How about the cooling method? Right. We can have the engine that use water to cool down the engine, or we can use the air to cool down, or we don't need to cool down the engine, right? Which is called the uncooled engines. Okay. How about the engine speed? The engine speed. This is very important for the diesels, right? The diesel engine, right, will run on different speed according to the different applications, not according to the speed of the car, right? Because people say, oh, slow speed, that means I run the car slowly. Medium speed, I run the car at medium one, or high speed, that means I run the car, right, at the high speed one. No, right? When we talk about classification according to the engine speed, right, it means it have to classify according to this because of the application here, right? You can imagine if you use the engine for the car, what are the normal speed that you use? Near 1,000 RPM and higher than 1,000 RPM, correct? Now, if you use for the aircraft, you never go below 1,000 because with that below 1,000, your aircraft cannot fly, right? You have to go for, let's say, more than 3,000 RPM. That is the starting RPM of the engine. For the marine, for the ship, right, you never go for over than 500 or 600 RPM because the engine will not provide enough torque to push the ship to sail. Okay, and for the power generation engine, right, you never run the engine higher than 3,000 or 4,000 because your voltage will be what? Deviates from the normal one. Okay, so this is what they mean the engine speed here, right? It's classified according to the applications, right? So we have the slow speed engine that the engine will never go above 400 RPM. Right? This is normally used in the ship or in the marine application. We have the medium speed, right, which is about 400 to 1,200 RPM. This is normally used in the engine that run the generator. And in the high speed, which is more than 12,000 RPM. This is used in the transportations. Okay. Classify according to the type of the fuel used. Right. Engine can use what? The gasoline engine. So that means they use the gasoline fuel or the benzene fuel. The diesel, they use diesel fuel. Right. The gas engine use what? The compressed natural gas, the liquid petroleum gas, and the alcohol engine use purely alcohol, which can be either ethanol or the methanol. Okay, right. This is classified according to the fuel use, right? And the last one, classified according to the cylinder arrangement. How do you arrange the cylinder in the engines. Right? There are many types of arrangement according to this. Okay. For example, here you have the inline cylinder, show right here. Right. That means you put the cylinder in line. Okay. Okay. You have a V engine. Right. You may have the W engine right here. Right. You can have a flat opposed or boxer engine. That means cylinder on the opposite side of one another. Okay. You have an X engine here. Right. And you can have a different radiant engine look like this. Right. All of these are called different radiant engine. Right. Because it can be either inline radiant engine. That means you have more than one cylinder inline. And also you have cylinder in along the radiant here. Right. So you can imagine this is more than 10 or 20 cylinder altogether here. Right. You can have a radiant engine, just only one line of one cylinder per radiant, not many cylinder per radiant here. Right. You have a double bank radiant, that means you have two radiant, right, attached with each other, right, or four banks. You have four radiant engine altogether right here. Okay. You have a double bank inline. Instead of just one line inline engine here, you have two inline engine right here. Right. Same as you have a H engine, which is a double fat opposed or the boxer engine. Okay. And a double shaft, it's hardly to see how it works right here, but I will show you later on. You have a delta engine, right? Then you have a rotor or a disc here, or even a swash plate engine, right? Where this will move, not their motion is not in one plane. Their motion when it moving is not in one plane, it's in multi-plane, right? In order to control the timing of the cylinder here. Okay. Okay, all of this I will give you the animation here. Right. In here, you see how the inline engine works. You see the V engine work like this. The crankshaft rotate. Okay, the W engine. Right. The boxer engine. The X engine, 4-cylinder. And the inline radiant engines. Right. Similar to the X engine, but you have more than 4 cylinders. Right. This is a double bank inline engine. You have 2 crankshafts. The head engine also have 2 crankshafts. Right. The delta engine, you have 3 crankshafts altogether. Yeah. Okay. And this is the double shaft opposed piston. Right. You have one shaft at the top here, and you have another shaft at the bottom. That's why they call it a double shaft opposed piston. Right. Opposed is mean in opposite directions. And this is called the swash plate, right? That you can see this plate move in different plane in order to create a different timing for this piston. Right. So this piston, they move up and down, right, in different time, not at the same time. Okay. Okay, so this is the radiant engine, right? And I show you how different it is between what we call the radiant engines and the rotary engines, right? For the radiant engine, right, you can see that the cylinder is fixed. Only the crankshaft is moving, right? But for the rotary engine, the cylinder is rotating, but the crankshaft is fixed. Okay, it's not rotating. Okay, so that is the classification of the internal combustion engines. Okay, now let's look at how the engine is operating. How the engine is operated. Okay. The characteristic of the engine operating cycle is that the piston move up and down in the cylinder, right? Everybody know that the piston go up and down, and it will transmit the power through what? The connecting rod. The connecting rod with this portion, right? This connecting rod will connect to the crank mechanism. Right? The crank mechanism is this. This is what we call a crank. This is what we call the connecting rod here. Okay, it will connect with each other, right? And to the drive shaft, here, right? In order to deliver the power, right? To deliver the power, we always need a shaft. This is the most important equipment, right? In order to deliver the power. Okay, this operating cycle is occur to what? A cyclic piston motion, right? So the piston will keep on going up and down. This is what we call a cyclic piston motion, going up and down, right? Which is produced by what? A steady rotation of the cranks, right? We need this crank. That's why our shaft need to have a crank attached on it. Without this crank, right, our piston will not have a steady motions. Okay, so this crank is to balance the motions of the piston when it moves up and down within the cylinder. Okay. Before we go to the engine operation, let's study some basic geometry of the reciprocating internal combustion engines. Right? And we know that we have a piston and a cylinder, and we have the motion of the piston. Right? So since the piston move, right, due to the movement of the piston, it creates three types of the volume in the cylinder. The first one, we call it V sub C. This is called a clearance volume. This is the space where the piston never reach, okay, never go beyond. Okay, it's up right here, right? The space here where the piston cannot go through, right? We call it the clearance volume. Okay, and then we have VT. VT is the maximum volume. Maximum volume. Maximum volume is what? Is the maximum volume of the cylinder. Right? We don't concern about the motion of the piston. We only concern the geometry of the cylinder, how big it is. Right? And use this geometry to calculate the maximum volume. Okay. And then we have a displacement or the swept volume. The displacement or the swept volume, we call it V sub D, or some textbook called V sub S, because S stand for the swept volume, D stand for the displaced volume, right? And this displaced or the swept volume is the difference between the maximum volume and the clearance volume. Okay, now come to the reasons why we always have a clearance volume here. Why we need to have a clearance volume here. Okay, if you remember in thermodynamics, if you remember this picture, right? This picture tells us that every time that we try to reduce the volume close to zero, this will happen, right? This will happen. The uncertainty amount of the physical parameter always happen. Right? This is something that we do not want to happen. Right? We want something that look like this, something that we can determine, something that we can be sure of the value. Right? But if you try to reduce the volume to get close to zero, you won't get any sure amount of the physical parameter. It keeps fluctuating, right? And this is the reason why we need to have a clearance volume here. Not because of the manufacturing technologies. No, no, nothing related to that, but because of the physical phenomena here. Okay. Okay. Then another parameter is the volumetric compression ratio. The volumetric compression ratio is the ratio between what? The maximum volume divided by the clearance volume. Okay. This term is always a confusing term for the student that pay no attention, because this term is called volumetric compression ratio. Sometimes they call it, in short, just a compression ratio, right? And every time that they call a compression ratio, students sometimes think, oh, it is a ratio of the pressures, right? They forget to look at the problem. This is the problem of the internal combustion engine, right? And in that problem, they said, this engine has the compression ratio equal to this. And then students with no attention, oh, they said compression ratio. So it must be the ratio of the pressures because it's compressed, right? But they are not, right? So remember, in the internal combustion engine, right, when we talk about the compression ratio or volumetric compression ratio, it is always the ratio of the volume, not the pressures, okay, for the internal combustion engine. Okay. Okay, so that is the basic geometry, right? We have three volume, we have the compression ratio, and we know where the volume is. Okay, so let's look at the working cycle of the engine, right? It's created because of the movement of the piston, right? So let's first look at the four-stroke engine, right? The first stroke we call is the intake stroke. Okay, the intake stroke. The intake stroke happen what? Happen when the piston is going down. The piston is going down. Right? So when the piston going down, the inlet valve here open, or sometimes they call it the intake valve. Intake valve here open, right? So since the piston is moving down, so they create a suction in here, suction condition in here. So when the intake valve open, the air or the air fuel mixtures can flow in the cylinder easily. So this piston is drawing the air or the air fuel mixture into the cylinder during the intake stroke. And after it draw the sufficient amount of the air, then the piston will moving up, right? Or in other words, when the piston reach down the BDC here, BDC stand for the bottom dead center, right? This is the far most that the piston can go down, right? When it reaches at the bottom dead center, it will change the direction, right, to start moving up. So when the piston start moving up, inside the cylinder already have the fuel air mixture. So, and these two valves are closed, right? So the compression stroke happen. The compression stroke happen. So the air or the air fuel mixture inside here is being compressed. What happened is the temperatures and the pressure of the air or the mixture increase, right? Increase. And what happened next? The next one is the combustion. Right? They said combustion usually start at the end of this compression stroke. Right? But in fact, compression starts a little bit before the compression stroke. Right? But theoretically, when you learn thermodynamics, we always let the combustion start at the end of the compressions. But in the actual cycle, the combustion always start at a little bit before the end of the compression stroke. Okay. Then after combustion happened, okay, after combustion happened, the expansion stroke happened. Okay, this expansion stroke not happen immediately, right? Because the major part of the combustion happened when the piston is still close to the top dead center, as I mentioned, right? The piston still moving up and the combustion happened. Right? So when combustion really happened and the exhaust gas that happened after combustion have enough force to push the piston to go down, then the expansion stroke happened. So normally we will consider that the expansion stroke happened when the piston start to move down. Right? It moved down because of the combustion gas work against the piston, while the piston, while the cylinder keep expanding. Right? The gas inside keep expanding. Okay. So the expansion stroke is that the piston keep moving down here. You can see that both inlet valve and exhaust valve still closed. Okay. Then when the piston move down to the bottom dead center, it can move down any further, so it start moving up. Right. The exhaust valve open. Right. So the exhaust stroke start. Right. The piston keep moving up and push the burn mixture or the exhaust gas to fall out of the cylinder. Right, so the cylinder become empty again, waiting for the intake valve to open and the air or the air fuel mixture to refill again. Okay, so this is the animations of the four-stroke engine. Right, different cycles, different cylinder here will work in different stroke. They work in different stroke here. Okay, so in overall, the four-stroke working cycle will complete into crank revolution. That means the crank have to rotate twice, or 720 degrees of the crank angle happen in order to finish one cycle, right? And the intake and the exhaust stroke, right, where we let the air and air fuel mixture to flow in and where we let the exhaust gas to flow out. These two strokes together we call the gas exchange process or scavenging process. Okay. So in overall, the characteristic of the four-stroke engine are what? The four-stroke of the piston and two revolution of the crankshaft. There is only one power stroke in every two revolution of the crankshaft, right? Because there is only one expansion stroke in one cycle. So there is only one power stroke happen. That's why this four-stroke engine require a heavier flywheel. Without this flywheel, they will have a non-uniform turning movement. Or in other words, the piston will not go up and down smoothly. Okay, so they need this flywheel to restore the power and release the power to the stroke. that have no powers to move, right? Okay. The power produced, of course, is less. It's less, right? Because there is only one power stroke. And the engine is heavy and bulky type, right? Because there are more moving parts for the for the four-stroke engine. Okay. The good thing is this engine requires lesser cooling and lubricants. Lesser cooling and lubrication. So we need less fluid. And it have a longer lifetime because they have less wear and tears. Right. This exchange form a complications of the engine because they have valve and also valve mechanism to control the opening and closing of the valve. Right. More expensive because more components. Okay. The volumetric is higher because they have a more time for induction, right? They have a fully intake stroke to draw the air or the air fuel mixture into the cylinder, right? This will make the volumetric efficiency higher. And that means the thermal efficiency is higher as well, right? And result in also the part load efficiency is better. Okay. So in overall, if you consider to use the four-stroke engine, that means you think that the efficiency is important, and that is happen nowadays, right? And that is happen nowadays because we are looking for a higher, a better engine efficiencies. Okay. How about the two-stroke engines? Right? Even though most of the engine nowadays no longer use the two-stroke engine, right? It used to be popular, especially for the motorcycle in the very beginning. Most of the motorcycle in the very beginning, they use two-stroke engine because it's more compact, less components, okay, and cheaper. Okay. Okay. So this two-stroke engine, a good part of the two-stroke engine is that it gives a higher power output for a given size of the engine. This means what? If you bring the same size between the four-stroke engine and two-stroke engine, right? The two-stroke engine will give you higher power than the four-stroke engine. Okay. And valve design is simple. The design of the valve to let the working fluid flow in and out is much more simple than the four-stroke engine. Okay. Now let's look at the engine operating cycle. The first one is the compression stroke. Right. So you can see that there is no intake stroke. Right. It starts with the compression stroke. So during the compression stroke, right, look at this picture. Right. It has the inlet valve here and the exhaust port here. Okay. Imagine that inside the cylinder already have the air or air fuel mixture in here. Right. So during the compression stroke, the piston move up. Right. When the piston move up, it close the exhaust port, and it also close the transfer port here. This transfer port is used to be a passage for the air or air fuel mixture that come in from the inlet valve to flow into the cylinder, right? So when the piston move up here during the compression stroke, right, it will close these two ports together along the way that it move up. So the volume inside here become a closed volume. So the compression happen, right? And again, the temperature and the pressure of the mixture rise, and then the combustion start at the end of the compression stroke or near the top dead center. This is the far most that the piston can go, the top dead center here. Okay. And after the compression stroke, right, ignition happen or combustion happen, then the second stroke will be the power or the expansion stroke. Okay. The major part of the combustion happen, right, when the piston is still right here or near here. Right? And when the combustion happen, again, the combustion gas will push the piston to go down. Right? So the expanding happen. So when the piston go down, the exhaust port open. This will allow the exhaust gas to flow out. And in the same time, the transfer port open. This will allow the air or the air fuel mixture to flow in. So in here and out here happen at the same time. Right? So the gas exchange process happen. Right? When the piston keep moving down and down and down until it reaches the bottom dead center here. Right? Because the air fuel mixture are already waiting in here to flow in when this open. Okay, when the transfer port open. Okay. So the gas exchange, as I mentioned, right, will begin when the exhaust port here open and the exhaust discharge, right, and the inlet port here, right, open to get the air and fuel mixture to flow in, and this transfer port open to let the air fuel mixture to flow in, right. So the gas exchange process or the scavenging process happen. Okay, and the condition that the scavenging process can happen is only when the pressure in the intake port here, the pressure that come with the air fuel mixture or the air, right, through the inlet port here, the pressure have to be higher than the pressure in the cylinder. Otherwise, this air or air fuel mixture cannot flow into the cylinders, right? The exhaust can easily flow out already because it outside here is the atmospheric pressure, right, which is lower than the pressure inside the cylinder, right? So the pressure of the working fluid that flow in here have to be higher than the pressure inside this cylinder in order for the scavenging process to happen. Okay, so this animation show you how it works, right? How it works. You can see that here, right, the transfer port is here, the exhaust port is here. So you can see the blue and the red mixed together in here, right, during the expansion process, expansion stroke. Okay, so since we talk about the scavenging process, so it's better to talk how many types of the two-stroke scavenging that happen, that can happen. Okay, the first picture is called a cross scavenging. Remember at the beginning we already mentioned the cross scavenging. Now we look in more detail how the cross scavenging look like, also the loop scavenging and the uniflow or through scavenging. Okay, the first picture represents the cross scavenging, right, where you can see that we have one port on one side and another port in another side, right? These two ports are opposite to each other. One port is for the fuel and air mixture to flow in, and another is for the exhaust to flow out. Remember, the scavenging process happens during expansion stroke. So this piston is moving down, right? So these two ports open. Inside here, we have the exhaust gas, right? And when this port open, the fuel and air mixture flow in and push the exhaust here to flow out. If it flow like this, is called the cross scavenging. How about the loop scavenging? For the loop scavenging, we have the exhaust around the cylinder. These are considered to be the inlet port. The inlet port here, not the exhaust, the inlet port here. And the exhaust is on the side of the cylinder here, right? So the air and air fuel mixture flow in and out like this, right? Every port here, you have the line like this. Wow. This is called the loop scavenging. Okay. The last one, uniflow scavenging, right? You have the inlet port all around the surface of the cylinder. Okay. And the exhaust valve is on the top. So the air fuel mixture flow in and push all the exhaust to flow out at the top, right? Not at the side like the first two one. Okay, it put the exhaust to go out at the top. This is called uniflow scavenging or through scavenging. Okay, so the overall characteristic of the two-stroke engine is what? There are two strokes of the piston. Okay, the piston move up and down to complete the cycle. Or in other words, there is only one revolution of the crankshaft in order to finish the cycles. There is one power stroke in each revolution of crankshaft, right? So every time that the crankshaft rotates, they have power happen. That means this two-stroke engine require a much lighter flywheel, right? Because they already have a uniform turning moment. The reason why they already have a uniform turning moment because they already have a power stroke at every revolution. Okay, so theoretically, the power produced is twice than the four-stroke for the same size of the engine, correct? Because every revolution you have power from the two-stroke engine. While for the four-stroke engine, you have to wait for 2 revolutions in order to get the powers, okay, out from the engine. And the engine is light and more compact than the four-stroke engine. But since it have power every time, right? So it requires a greater cooling and greater lubrications, right? And since it works very hard, so it have a higher rate of wear and tears, right? It needs no valve. You can use the port arrangement to do the scavenge, right? It's cheaper because less components, right? But the bad part about this two-stroke engine, even though they give you higher power, is that the volumetric efficiency is less because you have less time for induction. See, we don't have a truly or a fully intake stroke for the two-stroke engine, right? It happened during expansions, okay? So the volumetric efficiency is less. And that means the thermal efficiency is also low, right? And pass load efficiency is even worse. Okay. So in overall, if you consider to use the two-stroke engine, you use it when you have less money, right? Because it's a low cost. You use it because your space is so limited, right? So you look at for the compactness. And you use it because you don't need to have a bigger support for the engine because you require the light weight of the engine. Okay, so that is the engine operating cycles for both four-stroke and two-stroke engine. Okay, now let's look at the engine component. Okay, we start first with the spark ignition engine. SI stand for the spark ignition engine. And this is the 4-cylinder inline engine, which is the most common engine in the car. Right? For ordinary car, you see the inline engines, four cylinder. Right? 4 because this is 1, 2, 3, and 4. Right? Okay. So the component in here is what? I just show you the main components. I start with the air cleaner. Inside here we have the air filter in here to filtering out all the dirty part from the air that we're gonna take into the engines, right? And this is where the mixture happen, the carburetor, right? Modern car no longer use carburetor, they use the injector in here, okay? And below here, we have a camshaft. It's a shaft with the cam. This is the cam, right? This cam is used to do what? This is the clock or the timing, provide the timing for the engine, right? So that this is off cylinder here, right, will work properly according to the stroke in the cycles, right? So this is very important component. Is the camshaft. It provide the timing, right? Timing received from where, right? Received from here, the whole portion here, right? Determine this is the component to determine the time. This camshaft receive the time and give it to the cylinder. Okay, so this provide the time, right? Okay, it consists of what? The cam sprocket. We call it a cam sprocket here. Okay, it's a timing belt and the timing belt tensioner. This provide the tension to the timing belts, right? So the belt have to be under the tension all the time in order to provide the accurate timing. Okay, and then this is where the timing happen. Okay, the crankshaft sprocket here, right? So the crankshaft will send the timing to the crankshaft sprocket, to the timing belts, right? The timing belt can always keep the timing because of the tensioner here, and then it will send the timing to the camshaft here. The camshaft, after receive the command, it send or it force the cylinder to work according to the timing that the crankshaft provide here. Okay, and below here is the crankshaft, right? It's a shaft with the crank attached on the shaft, so it's called the crankshaft here. Okay, underneath the piston we have a connecting rod here, already mentioned. We have the exhaust valve, the intake valve, right? And the mechanism that move the valve is the locker arm and the hydraulic adjuster, right? The valve can go up and down because of this locker arm, right? And this locker arm will attach to the camshaft. Yeah. Okay. For the hydraulic adjuster, we will talk into the next slide. Why do we need this hydraulic adjuster? Below here, you see the oil pump or the lubrication oil here, and you have an oil pickup here. So that means underneath here is the sump for the lubrication oil here. Okay. Okay. This picture show you the hydraulic valve adjuster. Right? The reason we need this hydraulic valve adjuster because this to adjust the valve position here. Right? Even though we have the locker arm, we put the valve into the proper position already, but remember this valve operating all the time when the engine operates, right? So some wear and tear might happen on the valve tip here, right? So this will reduce the accuracy of the timing because this portion, the valve tip here, may be worn, right, or torn. Okay, so we need this hydraulic valve adjuster to ensure that the timing is always correct, even though this valve tip is already worn or torn, right? So this hydraulic valve adjuster is a must. Okay. Okay, so now let's look at for each component in more details. Right? The cylinder first. Right? Cylinder is the main part of the engine in which the piston reciprocate. Reciprocate means move up and down, to and from inside. Right? It usually make from a high strength material in order to withstand the high pressure that happen inside due to the combustions. And you can see the amount of pressure is higher than 50 bar or 5 megapascal, right? 50 bar. Right? And the temperature, look at the temperature, is above 2000 degrees Celsius that happen. Okay. Okay. For ordinary engine or the most common one, it usually make from the cast iron. Right? But for heavy duty engine like a trucks, a big trucks or a trailer, a big trailer, right? They usually make from the steel alloy or the aluminum alloys, right? And if you have more than one cylinder engine, which usually happen, right? Most engine have more than one cylinder, right? When you have more than one cylinder altogether, right? These cylinders are normally casted in one block known as a cylinder blocks. Right? They do not cast the cylinder one by one. They cast it all together in one block. Right? And this is what we call the cylinder blocks here. Okay. And it usually made from the gray cast iron because it have a good wear resistance and also the low cost. Right? Sometimes they use aluminum because the good part of the aluminum is that it have a light weight, right? For engine that concern about the weight here. Okay, the next component is the cylinder head, right? This is the part that cover the top end of the engine cylinder, right? Where you can see the inlet valve and the exhaust valve and the spark plug or the injector mounted on this cylinder head. Okay, this show you the picture where all these or this that I mentioned, they are positioned in the cylinder head. Okay, you see the valve clearance adjuster is right here. You see the locker valve here, locker arm here, right? That pivot to open the valve. Right? You see the locker shaft, that the locker arm attached to the locker shaft. You have a valve retainer or the valve tip here. Right? You have the spring. Right, the spring on the valve. This is used to close the valve here. Oh, I see this. Please remove this window away from the chair application. Every time it happens when people come in and out. Okay, so okay, it's got spring close valve here. Right, this is or used to force the valve to close when there is no action from the locker arm. Okay, so when there is an action from the locker arm, the valve will open, right? And when there is no action from the locker arm, the spring will force the valve to close. Okay, and we have the intake port here, right? And this is for mounting the thermostat here, right? To measure the temperature of the cooling water. Okay, on the cylinder heads, we have a gasket. Right. This gasket is to provide the seal between the engine cylinder and the cylinder head, right? In order to ensure the airtight joints between these two components, the cylinder head and the cylinder blocks, right? We have a gasket here, right? The gasket is usually made from a solid copper. That means one layer, right? If you use a solid copper, it's very expensive, right? So nowadays they use a multi-layer steel, right? And normally they have 3 layers altogether, like the one I show in here. They have a top layer, the stopper layer, and the bottom layers, right? The top and bottom layer, they are fully coating, right? Coated, right? And stopper layer, right, is used to stop the leakage from the cylinder to the cylinder head. Okay. This is called a gasket. A crankshaft. The crankshaft is used to convert the reciprocating motion of the piston, right? The up and down motion of the piston, and convert this to the rotary motion, right? With the help of the connecting rod, because it's connect with each other. The crankshaft is usually made from the steel alloy, right? And it's called the crankshaft because it has an eccentric portion that we call is a crank. Okay. So this is the crank. You can see clearly right here. Okay, and underneath the crankshaft, we have a crankcase. Right? This used to house the cylinder and the crankshaft of the internal combustion engine, and is also served as a sump for the lubricating oil. So you can imagine that inside here, they fill up with the lubricating oils. Right? Next is the piston. The piston is used to transmit the force exerted by the burning of the air fuel mixture or the charge. Sometimes we call air fuel mixture, sometimes we call a charge, right? In short, right? So it transmits the force from the burning charge to the connecting rod. Right? Usually the pistons are made from the aluminum alloy. Right? The reason because this aluminum alloy has a good heat conducting properties and also have a greater strength, right, in both mechanical and thermal. Because imagine that not aparting from the force that exerted by the burning of the charge, there also the heat that come out from the combustions, right? So the material that used for the piston have to have a good strength in both mechanical strength and thermal strength, right? Especially at a very high temperatures, not at normal temperature, at a very high temperatures, right? For large engine with slow speed, right? So the force and the heat is not that high, right? Slow speed. Sometimes they use cast irons instead because it's cheaper. Okay. Okay. On the pistons, right? We also have the piston ring, right? The piston ring is positioned on the circumferential groove that is provided on the outer surface of the piston, right? So on the side of the piston, you will see the ring, right? These rings are made from the steel alloys, right? And this steel alloy have to be able to retain its elastic property at a high temperature, right? So the elastic property have to be existed, right, at high temperature. Otherwise, it will not do the functions that it's supposed to do. Okay, there are 2 types of the rings, and then you will know why it have to retain the elastic property. The first one is compression ring. The second one is the oil ring. Right. The compression ring here, right, its function is to ensure that we always have the airtight seals, right, happen to inside the cylinder, right. Make sure that there is nothing leak out from the cylinders, right, to the place that is not supposed to go to, So this compression ring is used to prevent the leakage of the burn gas into the lower portions of the cylinder, right? So that's the reason why it have to be able to retain the elastic property here, right? Otherwise, it cannot provide the airtight seal here. How about the oil ring? The oil ring is the lower ring. Compression ring is the upper ring. Low oil ring is the lower ring. Right? This will provide the effective seals to prevent the leakage of the oil. Right? So upper ring provide the airtight seal to prevent the leakage of the burning gas. Lower ring to prevent the leakage of the oil into the cylinders. Right? So they separate these two. Okay. This picture show you the top ring, which is the compressed ring, compression ring. The bottom ring is the oil ring, and show you how the connecting rod connect with the piston and connect with the crankshaft. Right? They use a pin, not a screw. Okay. They use a pin. Right? The upper pin we call is the Gangian pin. Right? The lower pin they use a crank pin. Okay. Why they do not use a screw in both upper end and the lower end? Why? Anyone know the reason why they do not use the screw, or why they do not weld it? In order to make sure that it will not lose. Instead, they're using a pin, just a pin. The upper one called the gadget pin, the lower one is called the crank pin. Why? Attention student. Any question, any answer? If no, say no. โอ้
ครับ
หลับหมดหรือเปล่าเนี่ยสงสัยถ้าจะหลับหมดเว้ย รู้ไหมทำไมครับไอ้หมุดพินเนี่ยแปลว่าหมุดนะ because they would like to provide a flexibility when the piston is in motion along with the crankshaft here, right? So it cannot be tightly fixed in both ends. Cannot be tightly fixed in both ends. So pin is suitable for that because when you use pin, you allow a little motion that can happen, right, between two connections. A little motion between these two connections, because you know that the piston have to move up and down within a confined space. Okay, so you provide some room for flexibility of the piston when it moves into the cylinder along with the connecting rod, and also provide some flexibility when the connecting rod move along with the rotation of the crankshaft. Remember, the connecting rod move in the linear motions and the crankshaft move in the rotational motion, right? So you need to provide some flexibility between these two motions when it connect together. Okay, the next one is the connecting rod. Okay, connecting rod is used to convert the reciprocating motions of the piston into the rotational motion or the circular motion of the crankshaft, as I already mentioned. Okay, the little end is connected using a gadget pin, right? They call it a little end, right? With it, the end portion that the rod is connected to the piston, right? They use the gadget pin. And the big end, where the connecting rod connect with the crankshaft, they use a crank pin, right? The connecting rod usually make from a special steel alloy or the aluminum alloy, right? For the connecting rod. Okay. The next one is the flywheel, right? Flywheel is a big wheel mounted on the crankshaft, as I already mentioned, right? This is the mechanical battery, right? To restore the energy and release the energy due to its motion when it needs, right? So its function is to maintain the constant speed of the crankshaft, right? If you remove the flywheel out, right, you will see that your crankshaft will rotate in constant speed, right? So this flywheel is used for that because it restores the engine and it restores the power and provide the power, right, to the crankshaft. The crankshaft can keep its rotational speed here. Okay, so again, here I already mentioned this is done by storing the excess energy during the power stroke, with it return during after stroke. Okay, so this is the function of the flywheel. Okay, so that is the typical component for the SI engine. Okay, for the CI engine, they also have the same components, right? Same component. So I will not mention in detail on the component of the CI engine, but I just want to show you some that difference from the SI engine, such as in the SI engine, you see the carburetor, but for the CI engine, there is no carburation at the very beginning of the invention of the engine, right? So they have the fuel inject part start from the beginning, right? Start from the invention of this engine. They have fuel injection part, which is right here, right here. And they have the inlet port, right? And the inlet port here show is a loop type, right? No valve, the inlet port here, right? They have only the exhaust valve here, the locker arm here, and the locker arm here, right? Cylinder head, they have piston, crankcase, the same, and they have a fork connecting rod connect to the piston, so right here, and they also have the oil pan sump, so right here. Okay, so this is a typical component, right? Pretty much similar to the SI engine, only some parts such as the fuel injection part, the air inlet port. Okay. Okay, so okay, so this will be the last section of this lecture. The spark ignition engine operations. Spark ignition engine, right? In short, we call it the SI engine. Sometimes we call it the auto or the gasoline engine. Right? It is operated when the mixture of air and fuel ignite with a spark. So they require a spark plug to ignite in order to create the combustion. Right? So when combustion happens, we have a flame happen. Right? This flame will travel. Right? What we concern is on the flame front, how far that it travel, or how long that it can travel to the combustion chamber, right? The time that it travel is 50 to 60 degrees of the crank angle motion, right? We refer to the crank angle motion for the time that this flame front will propagate to the combustion chamber, because this 50 to 60 degrees can be converted into the time, because we know the revolution per minute of the crankshaft, right? Since we know the revolution per minute of the crankshaft, then we can use this to convert from round into minute or into time, right? And this time will represent how much time that this flame front will propagate through the combustion chambers. Right? Usually, it will take about 50 to 60 degrees of the crank motion, crank angle motion. Okay. This spark ignition engine usually operate with the air-fuel ratio about 14.7. I think everybody remember this ratio. This is called the stoichiometric ratio, right? That means it requires a complete combustion, right, to ensure a reliable combustion. Okay, so let's see how we can do the mixture in the SI engines. Right. The first method is by using carburetor. Right. For old engine, some old engine, you can see the carburetor in the engine. Okay. The carburetor is very simple mechanical and very most reliable mechanisms or most reliable device because it runs without the need to provide the powers. Okay. Okay. This picture shows you the carburetor. It consists of what? Of one chamber here that contains the fuel. Right? The amount of the fuel in this chamber or the level of the fuel in this chamber is controlled by the float here. Right? Because when the fuel flow in, since it is a liquid, right, so it have a buoyancy force. This buoyancy force will push the float to float up. Right? When this fuel is at one certain level, this float will push the needle valve here to close. So no more fuel flow in. Right? Above the float here or inside the chamber here where there is no fuel, the pressure in here is equal to the atmospheric pressure because we have a balance tube vent here that connect the space inside the chamber here to the space outside, which is in the tube. Here, this force will connect with the tube here. Inside the tubes, we have first a choke here. At this position, the choke is considered to be open or fully open here. Okay. And below the choke here, you see two venturi. The first venturi is the pipe shape itself or the tube shape itself. This is called primary venturi. The second venturi is a small tube inside the main tube. It is a second venturi here. And inside the second venturi, we see a main discharge nozzle. That its function is to deliver the amount of the fuel into the second venturi. Okay. At the bottom here, you see a throttle valve. This throttle valve is used to, remember, the way to control the loading, we use the throttle valve, right? So this throttle valve is to control the amount of the air-fuel mixture before it flows into the cylinder. This throttle valve is usually controlled through the acceleration pedal in the car, right? So every time that you step on the pedal, you control the position of this throttle valve, which means you control the amount of the air-fuel mixture that flow into the cylinder. Okay. The choke here is usually fully open because it will let the air to flow in, right? And when the air flow in, it will flow through both the secondary venturi and the primary venturi, right? When it flow into the secondary venturi, it will create the suction at the throat here, right? And because of this suction happen right here, the fuel in the float chamber here can flow to the main discharge nozzles here, right? And you can see that the fuel flow in terms of the liquids, and then it atomize into a small particle near the end of the nozzle here, right? So that it can easily mix with the air here, right? So you have a rich mixture. Rich mixture, it means you have a higher air fuel ratio right here. And then when this mixture fall part to the second venturi, it do the second mix with the air that fall to the primary venturies, right? Okay. So it's mixed with another portion of the air, right? So that it will get a stoichiometric ratio here. Then we control the amount of this mixture through the opening of this throttle valve before it go into the cylinder. So this is how the carburetor works, right? The fuel flow in here, not only because of the suction here that draw the fuel, but also the force that driving the free surface due to the atmospheric pressure here also, okay? Okay, since carburetor is good in the sense that we don't need to provide any power in order for the carburetor to work. Everything happens naturally, right? So, right, at the very beginning, people do not think about the fuel injection system because the carburetor already works for them. They have a venturi nozzle to make the carburetor work. And if they want to use the fuel injection system, the word injection means what? High pressures, right? And at that time, engineer still have the problem with the material. We don't have the material that's strong enough to resist the high pressure due to injections, right? So because of these two, right? So the development of and implementation of the fuel injection in the spark ignition engine, right, is not so encouraged. Right? So people keep using carburetor because I don't need to provide power and the carburetor can do the work for me. Okay. So no more development in fuel injection system until people start to would like to get a better power to the displacement ratio. They want a smaller engine, but a bigger powers, right? In which the carburetor cannot give them this. The carburetor, if they keep on using carburetor, they never get a better power to displacement ratio, or small engine with a big punch, okay, cannot. So people turn to the concept of the fuel injection. So that means they are now willing to solve the problem that happened with the fuel injection system. And that's why nowadays, right, most of the engine use the fuel injection system. Right? There are three types of the fuel injection system due to the development of the fuel injection system. The first one, or the early one, they call it the intake manifold injections, or the single point injection, SPI. Okay, in which from this picture you can see that we have only one fuel injector, right, on in here, right, in the passage of the air or in the airflow channels, right, and then we have a throttle valve here to control the amount of the air fuel mixture, right. So the fuel injector here will inject the fuels, right, and mix with the air that flow along with, right, and then this air fuel mixture will flow through the throttle valve and go to different cylinders, right. So by doing this, right, the result is you will not get a precise amount of the fuel need, right, because everything depends on one fuel injector. Everything depends on how uniformly that this shaft can distribute the same amount of the air fuel ratio to each cylinder, right? So the accuracy is hardly happen, right? The reason why first they do this, because remember, this injection need a high pressure for the fuel to be atomized, right? The fuel have to be into a very small particle in order to get a better mixing with the air, right? So in order to change the fuel from a solid liquid into a small particle liquid, they need a high pressure here, right? And because of this high pressure, right, the material have to be strong enough to withstand the pressure that happens. Right? So at the beginning, they still don't have a good material on this. So they put only one fuel injector here. Okay. Later on, the second development is called port fuel injection, the PFI, or the multi-point injection system. Right? Due to the development of a good material, so now they can move the injector further down, get close to the cylinder, because now they believe in the strength of the material. Right? So they move the injector down here, close to the cylinder, and they brave enough to use one injector per one cylinder, not one injector per all cylinder at the beginning. Right? So by doing this, now you can ensure a little bit on the amount of the fuel that need in each cylinder, because each cylinder have their own injector, right? So the amount is pretty precise. Okay. Then come to the present one, the gasoline direct injection, the GDI, in which now they believe in the material that they make that is strong enough, super strong. So now they press the injector within the cylinder. So by pressing the injector within the cylinder, they can have a highly precise amount of the fuel that need in each cylinder, right? Okay. Compare with the previous one, just close to the cylinder, right? They still have friction barrier here that can reduce or change the amount of the fuel flow rate. Different. If I talk the fuel amount, of course, it's the same. But if I talk about fuel amount flow rate, it's different. Okay. Okay, so in overall, the fuel injection is the most accurate method. Like people know this long time ago, but they dare not to use it because of the material problem. Okay, an important advantage of the direct injection is in the fact that what? The evaporation of the fuel takes place within the volume of the cylinder, right? The evaporation takes place in here. This evaporation will help the engine in terms of cooling down the cylinder, because when the fuel evaporates, right, it will draw the heat. Right? So the heat come from where? Come from the cylinders, right? And this will help cooling the charge or the mixture. And the result is what? Right? The result is you have a higher volumetric efficiency of the cylinder, right? Since the chart temperature or the mixture temperature is reduced, you get higher density of the chart or the fuel air mixture, and that means you can fill up more chart into the volume of the cylinder, right? Which means you have higher volumetric efficiency, and the result is you can have higher thermal efficiency. Okay, so come to the last one. I hope everybody still fresh. Still fresh, huh? Okay, this I show you the typical sequence of the event in the 4-stroke SI engine, the actual one. This is important, right? Because you will know what actually happened when the SI engine operates. Okay, I show you two graphs. The first one is about the pressure that happened in the cylinder, along with the positions of the piston in terms of the crank position and angles, right? That's why you see TC stand for top dead center, BC stand for bottom dead centers. Okay, so let's first look at the top chart here. Okay, start with IVO. IVO stand for inlet valve open, right? So at this position, right, the inlet valve start to open. It open when the piston is moving up near the top dead center, right? So imagine you see the piston moving up close to the top dead center, and then you see the inlet valve open. And when the piston move up to the top dead center and start to move down from the top dead center, then you see the exhaust valve close. Right? When the piston start moving down the top dead center, the exhaust valve close. So that means what? During this period of time here, both the inlet valve and the exhaust valve are both open, right? Right. Because you see the inlet valve close here. And when the inlet valve open, it is the start of the intake stroke here. Intake stroke here. So the intake stroke happen right, along the way that the piston keep moving down here while the inlet valve open and the exhaust valve close. Right. The intake stroke happen until the piston move to the bottom dead center, move down to the bottom dead center. After that, the piston start moving up. The intake valve still happen, not finished. Right. The piston start moving up until it move away from the top bottom dead center a little bit. The inlet valve close, and that means it is the end of the intake stroke. So the intake stroke happen on both the piston moving down and moving up. This is what happened in the actual cycle. And then after the inlet valve close, the volume inside the cylinder is closed. So the pressure increase, right? Because when the inlet valve closed, the exhaust valve already closed here. So everything is closed. The volume is closed. So the pressure start to increase as the piston keep moving up until just little bit again before the piston go to the top dead center, the spark happen. The spark happen here. Okay, so the spark happen before the end of the compression. The compression still happen, but then we spark, right? So the combustion start to happen at the point where the spark happen. See the combustion right here, right? So after the spark, you still not seeing a high rise of the pressure. The pressure keep going, but not going up so fast. Right? Just a little bit after the spark happened, then the combustion now really take into effect. So you see the high rise of the pressure going up here, as long as the combustion happened. Right? Until at this point, where the piston is at the top dead center, right? This point. After this point, the piston start moving down. But look at the pressure. Even though the piston is moving down, the volume in the cylinder start to increase, but the pressure still going up. This is truly the effects from the burn gas or the combustion that make the pressure increase. Right? So the pressure keep rising until this point, where the effects of the combustion start to subside or reduce. Then the pressure start to reduce. Right? So from here to here, the piston moving down and down and down. Right? Piston moving down and down. The combustion finished around here, no more. Right? The piston moving down and down, and the pressure reduced because the volume increased until this point. Just before the piston moved down to the bottom dead center, the exhaust valve open. The exhaust valve open. Okay, by the way, the compression finished when the piston at the top dead center. Right? And then when the piston start to move down the top dead center, the expansion stroke happen. Okay. So the piston start moving down and down and down, expansion happen. Right? The exhaust valve start to open here. At the point where the exhaust valve open, the intake stroke or the exhaust stroke happen. Right? So you see a portion of the overlap between the expansion stroke and the exhaust stroke happen right here because of the exhaust valve open. Right? Remember, the inlet valve closed already from here, right? So now, at this point, the exhaust valve open. The piston starts still moving down and down and down until it reaches the bottom dead center. And then the piston start moving up, right? When the piston reaches the bottom dead center, that is the end of the expansion stroke. After that, it is purely the exhaust stroke because the exhaust valve still open and the inlet valve close and close until it move up close to the top dead center, that the inlet valve open again. Right? And when it reaches the top dead center, after that it start moving down. Right? This move piston going up and up until it reaches the top dead center, and after the top dead center it start moving down. So it's the end of the exhaust. Okay, so this is what happened actually in the cylinder according to each stroke here: intake, compression, expansion, and the exhaust. The dashed line here represent the actions if we have no spark. Right? They call it the motoring curve. No combustion. If we have no combustion happen, right, the pressure will go along with the solid line here and then depart from the solid line to go along with the dashed line here if there is no combustion. Right? This is called the motoring curve. Right? No combustion, no spark ignition. The pressure inside the cylinder will go according to this motoring curve line. Right? In which you see some portion is the same as the combustion, but there are some portion that different if we have combustions. Okay. The graph down here show you the volumetric efficiency because it's the ratio of the volume divided by the maximum volume or the swept volume. So you can see the change of the volumetric efficiency along the way that the piston move up and down, and then up and down. Okay, so the volumetric efficiency change because the volume of the cylinder changes. And then the left graph here show you when the combustion happens. This show you the fractions of the mass burn, right? So you can see that at the beginning when the spark happen, right, only a small portions of the mass of the fuel that is burned. And then after that, it increased rapidly, highly increased, right? And then keep the same after that, right? After finish the combustions, no more. Okay. So this will give you the picture of what happened inside the cylinders. Okay, this show you the example of the spark ignitions. I give you several pictures, right? And the reason is because I want you to know when they specify the engine, these are the information that they need to provide, right? First, they provide the shape of the cylinders, 60-degree V6 SI engine. This is the information so that we know this is 6-cylinder engine and the arrangement is the V type. Okay. The second information is what? Is the capacity of the engine, right? The displacement is 2.8 liter and the size of the cylinder is what? The diameter is 89 millimeter and the stroke of the engine is 76 millimeter. Right? Another performance parameter is the compression ratio. Remember, see, they just make it in short, compression ratio, but everybody have to remember this is talking about volumetric compression ratio. It is 8.5. And the maximum power delivered from this engine is 86 kilowatt at 4,800 revolution per minute. Okay, so from this information, I just want to know that what is each cylinder volume. I know information about the bore of the cylinder. I know information about the stroke. So I make a simple calculation, pi b square over 2 square times with the stroke. Right. So each cylinder volume is what? 0.473 liter. Right. Time with what? 6 cylinder. Pretty much the same as 2.8 liter. Okay. Okay. This show you the turbocharged 4-cylinder SI engine. Right. If this SI engine equipped with the turbocharged. Right. So where is the turbocharged? Oh, I have this piece, remove this window away again. Okay. Anyway, this is the compressor. This is the turbine. Yeah. The compressor is driven by what? Driven by the exhaust gas that flow out. Right? The dark arrow here represent the exhaust gas that flow out from the cylinder. Right? It flow out via the weight gauge. The weight gauge is to determine the amount of the exhaust that how much that should go to dry the compressor and how much will be bypassed to the exhaust pipe. Okay, so this weight gauge is the function is to do this. So the exhaust gas will flow to the compressor to dry the compressor, and then it will dry the turbine, where the turbine will compress what? The fresh air that flow to the air filter, right? So this turbine will increase the pressure of the fresh air. So the pressure of the air after the turbine will be higher. So make it easier to flow into the carburetor. Okay, these engines have the intercooler here because when the turbine increase the pressure of the fresh air, it also increase the temperature. So in case that the temperature is too high, then we will use the intercooler to cool down the temperature of the fresh air. The pressure is still the same, but the temperature reduced. So it will go into the carburetor here, and then it go into the intake manifold, and then to the inlet valve, and then into the cylinders. Okay. This one show you the cutaway view of the turbocharger. We will have a lecture that cover this part. Right? This is the compressor, and this is the turbine here. Connect with the shaft here. Okay, so the last one will be the component of the Wankel rotary engines. Okay, the Wankel rotary engine. I just want to show you the component of the Wankel rotary engine. Above here show you the main components. Like we have a fixed, we have a side housing here, a side housing here. Inside at the middle, we have a fixed timing gear here. Then we have a center housings. We have a rotor. Right. In the center housing, we have the exhaust port, and we also have the intake port. Right. And on the edge of the center housing, and also on the edge of the side housing here, along the edge here, they have a coolant passage that will allow the cooling water to flow along the edge of the side housings and the center housings. Okay. And the rotor here, we have the internal timing gear inside the rotor. Right. And then we have the eccentric shaft, not eccentric shaft. This is the eccentric shaft because we have an eccentric here. Right. And then we have another side housings, and we have flywheel. This is a much, right, attached here. And below here show the operations of the Wankel engine, Wankel and engines. Right. They have induction or the intake. Right. In order to understand the movement, you have to keep your eye on one point in here, B. Right. That's why I put the letter B in list. Right. For each picture here, you only concentrate on B portion here of the rotor. Then you will understand. Okay. So induction, right? B is right here. So this valve open, the fuel mixture here. And then B move down here, right? This become a closed surface, closed volume. So compression can happen if the rotor move, right? Compression happen. And then when B move down to here, right? This portion already compressed. So it ignites. This portion ignite. Right? And then B go down to here is the time for the power to release. And then when B move up here, the product of combustion still here, right? Yeah. So when B move down here, the product of combustion, this is the time for them to leave the engines. Okay. So they have induction, compression, ignition, power, and exhaust, the same as other internal combustion engines. Only that every motion happen in rotational motion only, right? So they don't need to convert the linear motion to rotational motions. Okay. Okay, and this animation show you how it works. Again, keep an eye on A. Okay, concentration on point A, and then you will see how the working fluid is being treated in the engine. Okay, and this is the actual pictures of the rotary engines. Anyone know which is who is the car maker that make a rotary engines or the Wankel engine? Anybody know who is the only car maker nowadays that make a rotary engines?
Mazda
Oh, correct. ถูกต้องนะครับ Mazda is the only one. I still do not know why other car manufacturers don't go for the rotary engine. Only Mazda that they have been doing this, I think more than 40 years. 40 years. Okay. Okay, so I think that will be the end of our lecture today. Okay, so it's quite a long hour of lectures, no stopping, because there's a lot of material. And then what I believe is we do it hard at the beginning, and then we can do it soft at the end. This is my belief, okay? Because at the end, it means near the exam, right? Okay, so I don't want to spend time much on the lecture when it's getting close to the exams. Okay. Okay. So what? Any questions? Any questions? You can say no if you don't have any question, so that I can finish. But if you
เดี๋ยวโพสต์ให้ไหมครับ
what?
วิดีโอนี่เดี๋ยวโพสต์ให้ไหมครับ
Yes, yes, I do recording. But you have to be sure because this is a live broadcasting, right? I talk without script. Maybe I can be wrong. So when you look at this video, if you found anything incorrect, please tell me. Okay?
ครับขอบคุณครับ
Because it's no script. Okay, and it takes time to convert the recording into the MPEG-4. But anyway, I already do the record and I will convert it for you and post it into the Line group. I'm not putting this into my course view. I will put it into the Line group. Okay, so any questions? Say nay. Everybody say nay. So that I can end the meeting.
No.
Okay, normally they say nay. A and nay. A is mean yes, nay is mean no.
Nay
Pelosi, you see the CNN news. Okay, so see you next week. See you next week. Okay, I'm going to end the meeting.